go from one state to another. This is taken into account whenever search algorithm is finding a best solution to reach from point A to point B. What it tries is it tries to minimize this cost function so that I reach from my home to the college in the minimum possible time, and I should also cover the minimum possible distance to travel. The next is the heuristic function. What a heuristic function comes into picture only when we talk about informed search algorithms. Now we will look at what informed and uninformed search algorithms are in further. But basically, what a heuristic function is it is an estimate to which I will take from which is based on how much cost is required to reach the end goal. Now, for me, the heuristic function might be time. So, from my home to our college, it requires 5 minutes to reach. But that also depends on which road I take. If I take a longer route, it might take 10 minutes or 15 minutes. But the search algorithm will give me the optimal route so that I reach the college in optimal time and I don't waste my time in the traffic and in roads which are under construction. So this is how heuristic function works. The informed searching algorithms also take into consideration the heuristic function so that the optimal path can be calculated. Now let's look at what is informed search versus uninformed search. In uninformed search, it is also known as a blind search or brute force search. What uninformed search algorithms do are they look at the complete state space and search for all the paths that are possible to reach from the start goal to the end goal. And they choose the best optimal path that is available to us. Search strategies they are based on solely on the structure of the search space and do not consider the desirability of the specific state. What this line means that the uninformed search algorithms they take into consideration uh, uh, each and every possible path that can be generated from the start node to the end node. This requires a lot of computation and a lot of time. So even though they give us the optimal solution, sometimes the time required for these algorithms to process through the complete state space is much higher than what is the time which we are given. So suppose I employ the breadth first search algorithm, it will search the entire state space, so that it finds the optimal path from the start node to the end node. But I might only have 5 minutes to reach college and I have some important work at college. But if I employ the breadth first search, the algorithm might take more time to calculate than the time I need to reach the college. So this is not a viable option. Now let's look at informed search. In informed search, they are also known as heuristic search. They also take into consideration the cost it takes from me to reach from point A to point B, not just from the start node to the end node, but also between the start node and end node, there are multiple nodes. It also takes into consideration how much cost is required to reach from the specific node to the end node. And it incorporates domain specific knowledge or heuristics to guide the search process more efficiently. It prioritizes promising states and paths based on estimated costs. So if I have 5 possible paths I can take to the college, an uninformed search will look at all the 5 paths from the start, that is my house, and the end to the college. But an informed search uh, looks at the time which will required for each of this paths, and it will choose the best path to go from my house to the college. Examples of uninformed search would be a breadth first search and a depth first search. And examples of informed search are A star algorithm and greedy best first search. Now let's look at the A star algorithm in detail. Let's first a brief history and background is the A star algorithm originated in the Stanford Research Institute. It was developed by Peter Hart, Niels Nielsen, and Bertram Raphael in 1968. Evolution. The A-star algorithm evolved from the Dijkstra's algorithm and best first search. So the A-star algorithm actually takes both the concepts of the Dijkstra's algorithm and the best first search and combines them to make a more optimal algorithm, which also saves us time and memory space to calculate the path more efficiently. And the applications used in A-star algorithm is used in various domains, including robotics, video games, route planning, and artificial intelligence. Let's look at the functionality of the A-star algorithm. The A-star algorithm efficiently finds the shortest path from starting node to a goal node in a graph. So whenever we want to traverse a graph and we want to get from point A to point B, the A-star algorithm finds the most efficient path, looking at the cost to get to the middle node and also the cost needed from the middle node to the end node. It combines the benefits of both uniform cost search and greedy best first search. A-star algorithm also utilizes a heuristic function to guide the search towards the goal while ensuring optimality under certain conditions. Now, these are a bit complicated to understand, but it would be more clear when I give you the demo through Unity, which I have prepared. Now, what are the key components of the A-star algorithm? The A-star algorithm uses two functions. First is the cost function g of n and the heuristic function h of n. Let's look at what is the cost function. The cost function, it represents the cost of reaching a particular node from the start node. So now, if I want to reach the college, I take I have to take path A. Now there are two roads which I need to traverse when I go from my house to the college. So what the cost function is, that cost function is the distance of road A and road B from my house. That is the cost of going from my house to that road. The A-star algorithm takes that into consideration. And then the second is the heuristic function. The heuristic function is the cost from going from road A and road B to the final node, which is the college. And the evaluation function. Now, I like I said earlier, the evaluation function is the rule which I have to follow when going from point A to point B in the graph. The rule for the A-star algorithm is that it minimizes the sum of the cost function and the heuristic function so that the optimal path can be found from start node to the end node. The evaluation function f of n is simply the addition of cost function and the heuristic function. The A-star algorithm combines the cost and heuristic functions to evaluate the desirability of expanding a node. So whenever the A-star algorithm starts from node A, it looks at its neighbors and it evaluates the evaluation function f of n so that it can find the optimal path from point A to point B. Now let's look at the search process of the A-star algorithm. The A-star algorithm selects node for expansion based on evaluation function, prioritizing nodes with lower f values. Now that's the step followed by A-star algorithm. First, the A-star algorithm begins with the start node, and for each iteration, it looks at the neighbors of the current node. Now, first we start at the start node, and then the neighbors are looked at. The cost of going from the start node to the neighbor is first calculated, and then the cost of going from the neighbor to the end node is calculated, and the sum of these two values are taken, and that is the f value of the neighbor. And when we have all the neighbors of the current node selected, we of the current node calculated, we select the neighbor with the lowest f value so that we can continue this process iteratively. In the next iteration, I will go to the neighbor with the lowest f value, and then uh, again search for the neighbors of the current node and then calculate the uh, gn and f of n. The g of n is the distance from the start node to the current node, and h of n is the current node to the end node distance. And whenever I go from one neighbor to another, the A-star algorithm updates the cost and heuristic values for neighboring nodes and adds them to search the state space. And this continues till the end goal is reached. Let's look at optimality and the completeness of A-star algorithm. A-star algorithm is both complete and optimal. Now, what does this mean? Search algorithm, to be optimal, it has to give you the best optimal path to reach from goal point A to point B. What is optimal path? Now, optimal path means to uh, find the path with the lowest cost to reach from the start node to the end goal. And completeness. Completeness means that A-star algorithm ensures that A-star will always find a solution if it exists. Now, if even if there are barriers in between, from reaching from node A to node B, A star algorithm will find alternate routes so that new paths can be found. Comparison with other search algorithms, A star algorithm outperforms many other search algorithms because it is more efficient and it uses less memory space to find the optimal solutions. For if we compare it to the breadth first search also gives us the optimal path, but it requires more memory and also requires more time to calculate the route from point A to point B. The A-star algorithm balances between completeness, optimality, and computational complexity. A-star algorithm does not need to search the entire state space as it only looks at the neighbors with the lowest f values. This cuts out a lot of the state space and only looks at the nodes which are most desirable, and the undesirable nodes are never calculated, so the computational complexity reduces. And the A-star algorithms is adaptable, which means even if we remove a node in the graph, the A-star algorithm updates the path and takes the alternate route uh, with, with minimum computational complexity. Let's look at the unity demonstration of the A-star algorithm. Yeah, so I have it opened in Unity. Okay, so this is the Unity game engine. It uses C# scripting to make. This is basically used to make games, and I am a part of the game development club, Game Dev Utopia. So I am pretty well versed with Unity, and I use Unity quite often. So I was quite familiar with how Unity works, and after learning about the A-star algorithm, I was very curious of how to implement such algorithm in Unity itself, because I knew that A-star algorithm worked as the main pathfinding algorithm in video games, but I never knew how it worked. After I got to know how it worked, I was really looking forward to implementing it. So this was my first implementation. So if I run this, you'll see, yeah. So this is the orange circle is the starting position of the starting node, you can say, and the yellow circle is the final position. So, and the blue colored squares are the path taken from the start node to the end node. Now let's look at how A star calculates this path. First, I will start at the red node, and this is my starting position. I will first look at the neighbors of my starting node. So I will look at this node, this node, this node, and all its neighbors. Then I will calculate first the G cost. Now G cost is the all the numbers you're looking at the top left of each of these tiles. So here this 10, 14, 10, 14. These are the uh, G cost, which is the cost required to get from the start node to the desired node. So when I calculate this G cost, when I move diagonally, I need 14. The cost to move is 14, as the diagonal of a diagonal which we can calculate is the root 2 times the distance of the edge of the square. So from going from square A to square B diagonally would take me 14 cost. So then the edge cost is calculated. The top right number is the edge cost, which is the heuristic cost. Now, heuristic cost is calculated by taking the distance from the current node to the end node. So here the green colored node is the end node and the current node is here, which we are calculating. So from this node, I would require to go two spaces diagonally and two spaces horizontally. So that would add up to 48. So the edge cost going from this neighbor to this end node is 48, and this big number here is the f cost, or the uh, f- sum of g cost and h cost. So what the A star algorithm does is it looks at the neighbors of the current node and it chooses the neighbor with the lowest G F cost to move ahead. Now, as you can also see here that there are two nodes with the same F cost. Here the F cost is 52 and here also the F cost is 52. If this two neighbors have the same f cost, the A star algorithm also looks at the individual heuristic value of each node. So here we can see that the heuristic value is 38 and here it is 42. So if the f value of the two nodes is same, the A star algorithm chooses the node with the lower h value. So here we choose the uh, node with this 38 h value and 52 heuristic value. The next we will look at the neighbors of this particular node. So this particular node has 1, 2, 3, 4, 5, 6, and 7 neighbors. So yeah. So question from Abhishek: why the lower value? So what we want to do is we want to minimize the cost going from the starting node to the end node. So to find the best path from going from the starting node to the end node, we want to travel such that we require the lowest cost. That would give us the optimal path to go from point A to point B. So if I want to travel from the start node to the end node, the best path I would take is I would go diagonally upwards and then once to the right. So my path cost is reduced. So if I move the red square to the left, you can see the path updates, and I will now need to take three diagonal steps and uh, se- eight horizontal steps. So this is how it minimizes the path. I will also show you how it works if there are barriers in between and the uh, path is blocked from one side. So
Excuse me.
yeah,
What if you consider that 10 as a 1 and go forward? Then what will be the answer? Or what would be the path?
like
Here you
this,
considered 98 and went forward, right?
yeah.
Uh,
Yeah, so we want to reach the goal, right? So what the edge cost gives us is that the cost from reaching from current node to the end node. So I want to minimize my cost from going from current node to end node, right? So I will first choose the edge cost, as the edge cost gives me how far I am currently from this position to the end node. So I will always prioritize edge cost over the g cost, as g cost is just the cost going from starting node to this node. So that's why I'm choosing the lower h value first rather than the g value first.
okay,
And
got it.
yeah, and the f cost is the overall cost function. So overall I want it to be lower, and if those are similar, I will go with the one with the lower h cost, as that will put me closer to the end goal. Is your doubt clear?
Yeah, yeah, clear, clear.
Okay. So now suppose I'm starting at the lower left corner and going to the top right, and there are barriers in between. Suppose these are the barriers. So the A star algorithm also works and to go around barriers. So let's look how this works. Now, first, the route is calculated as normal from here to here, but at this point, it encounters a barrier. So, what the A star algorithm does that it knows that this path is unwalkable, as it has infinite costs. So, what it does is it looks for the neighbors which has lower h value, and it proceeds in that direction. So here it looks at the neighbors, and here all of them have the same h cost of f cost of 182, but here this node has the h cost of 100, which is the lowest among its neighbors. So it chooses this node, and then it goes to the it also checks its neighbors, and when it goes and checks its neighbors, there would be multiple nodes with the value 188. So it keeps searching for all the nodes with the value 188, and then it will choose such a node which will have the next node with lower value. So it will go from here to here and then here, as the h cost here is 82, and then it will keep searching further, and it will also navigate through different corridors and paths to reach the end goal. So I can even add more paths, so even that will be calculated easily. Now let's look at if there is no path. So if I block off the algorithm here, the A star algorithm does not find a complete path, and there is no path calculated, as you can see. So it will look at each and every possible space possible to find the optimal path. But It can never find the optimal path here in this case because there is no path. So the entire state space gets exhausted and the A star algorithm returns no path. It so the A star algorithm is adaptable also. So even if the path is not there, it will still search, and if the path is not available, it will tell us the path is not available and it will not calculate further. So this was a two-dimensional example of how A-star algorithm works. And I also prepared a 3D algorithm of how such an algorithm can be used in a 3D game. So let's look at a 3D example now. So this utilizes in the backend the same code which is the 2D algorithm using, but this just puts it in a 3D world with three-dimensional objects and three-dimensional seekers. And this object even follows the path of the target object. So if I run this here, you will see there will be path generated from the seeker to the target. Yeah. So when I run this, yeah, so this black line is the path calculated by the seeker to the end node. So this was how it would be in a 3D world. Now, whichever 3D game you play, the ground of the 3D level is divided into these grids, so which is used by the pathfinding algorithm to find the optimal path in the game. So even if the walls are moved, you can see the just a second. Unity just crashes sometimes. Huh, just a second, some technical difficulties. Unity just whenever in development can experience a few crashes, but whenever we build the game, it's quite stable. So yeah, so here we have the building. So even if I move these blocks, the game object can still find the new path to the target. Yeah. So as you can see, it navigates swiftly through the through the obstacles and finds the path. And it can also be done for multiple different enemies. So if you want to make a swarm of many enemies, so what I will do is I'll duplicate these a few times. I'll just put these all around the map. Yeah. So suppose these are all my seekers and they're trying to find a path to the player. So here is our player. So when I run this, all these different objects will find a path to the player. Uh, let's I'll now disable the grid so that you can see how what path they are taking better way. What it will look in the actual game. Yeah, so this is how it would look in the actual game. And the black lines they are following are the different waypoints in the algorithm. Now, as you can see, the path taken by these objects is a bit jagged rather than moving in straight lines. Now, this is because of some optimization techniques which are used, which make sure that less memory is used whenever multiple different objects are finding the path. So what we do is whenever the path has the same direction for a longer time, the complete path is not saved. Only the starting and ending of the path is saved. So the object moves directly from the point A to point B without searching in between. So let's look at what I mean here. Yeah, so whenever this path is calculated, so as you can see, for example, here, the game object would have to take only a very small change in direction here rather than going here straight, taking a right and then going diagonally. So what it optimization does is it checks if the change in direction over a long period is not much. It will only save the path where the enemy need to take a turn. So here the enemy needs to turn and here the enemy needs to turn. So only these 2 points are saved and the enemy moves in the straight line from here to here, and the middle nodes are ignored and they can be erased from the memory and memory can be saved. So even if I have thousands of different enemies following the player, like in a zombie games, for example, then I don't need to save all the different paths the zombies can take. I only need to save the nodes where the zombies would take a turn and follow the straight path. So only these points are saved. So if I run this here, you'll see. Yeah. So only the paths where the objects take a turn are saved and they find the path to the player. So these two are the demonstrations of H-star algorithm in Unity. Now going ahead with our presentation. Yeah, yeah, different displays. Yeah. So next we'll look at the practical applications of the H-star algorithm. So, as I mentioned before, the A-star algorithm is implemented in video games a lot, and it is one of the most popular algorithms for the pathfinding in single-player games as well as multiplayer games with non-player playable characters. In video games, developers frequently utilize H-star algorithm for implementing pathfinding and navigation systems in various game genres. So now, if you'd have played any game which involves NPCs which follow the player going from suppose for a mission, or the enemies which find the player even if the player hides behind walls. So in those games, the AI which is working in the enemies is using the A-star algorithm to find the optimal path to reach from their current location to the player. So in this way, the computational power is saved and the time is saved which is required to calculate such a path. And in games, the time to calculate a path is very important, as you know ki any if you're playing any game, any kind of lag only leads to frustration, and it can lead to you stop playing the game. So the developers have to optimize their game in such a way that their game does not lag, and it also gives us the best possible version of the game. The Acer the non-playable characters, such as in suppose Legend of Zelda, where we have our player Link, and we also have other NPCs which can either follow us or we can interact with them. So they utilize A-star algorithm. Then the Civilization 6. Civilization 6 is a turn-based strategy game in which there are small characters on our board which can follow the different paths in the game, and whenever we want to them to move from one grid cell to other grid cell, they use the A star algorithm to find their path. Then again, also a game which many of you would be familiar with, which you might have played in your childhood, is Age of Empires. So whenever we want to build some buildings in Age of Empires, we have to assign few workers to the building, and they will go make their path from their current location to the location where the building is being built. So that in that process they use the A star algorithm. And as you guys know, Age of Empires can get pretty crazy when you in the late game, where you have thousands of different workers working for you. You're a complete army, you have your ships, you have your battle equipment. So computing paths for all these different units is computationally very expensive if we go for any other algorithm. But the A-star algorithm optimizes both time and computational complexity so that even thousands of different units can find their path to to the location in an optimal way. Now let's look. These were the examples from the gaming world. Now in the real world, let's look at the applications of the A-star algorithm. So, beyond gaming, A-star algorithm finds extensive application in real-world domains such as logistics, robotics, urban planning, and transportation. In logistics, so whenever you order something from Amazon, the Amazon warehouse is not located in each and every city in the world. They have their central distributors and they have their other distributors which take the package from their warehouses to your home. So whenever Amazon wants to get the optimal path from their warehouse to your home, they can use the A star algorithm to find the optimal route which takes the least cost, which saves them money, time, and also gives the customer satisfaction. Next would be robots. Now, robot in robotics, there are two examples would be. First is in warehouses. Some robots are used to arrange pallets and uh, in the warehouses, different pallets and tools and inventory of the warehouse is handled completely autonomously by the robots. So how they do is the warehouse is divided into a grid of cells, and the robots find their path from cell A to cell B using the A star algorithm. And even if there is an obstruction in the way, that the path gets updated in the robot system, and all the other robots are also notified of the obstruction, and the A star algorithm finds a different optimal path to the new location. So the operation of the warehouse does not get halted, and money is saved, and time is saved. Next, in transportation, as I gave an example earlier of the GPS system, if I want to get the directions from my home to my college, I would use the A star algorithm to find the optimal path. So those were the real world applications of A star algorithm. So the conclusion would be just a recap. Through what we saw was how what are the search algorithms and what are the different types of search algorithms, and we looked at the informed search, uninformed search, and what they are. Next, we looked at how HR algorithm came to be and how it finds the optimal path from node A to node B. Then we've looked at the efficiency of A star algorithm, as A star algorithm both optimizes time and the memory required to calculate path. And we also saw the impact of A-star algorithm, whether in the virtual world of gaming, in different online games and uh, different scenarios, and in the real life, in robotics, in logistics, in route finding. So these was the applications of A-star algorithm. So thank you. That would be all from my side, and I'm open for question if you have any. Yeah, Sharad, you have your hand raised.
Yeah. Uh,
Yeah.
as you told, the historical algorithm in Unity,
Yes.
it finds the shortest path between A to B. But
Yes.
what if I want to include like a middle point? Like if I want to traverse from A, B to C. So does
Okay,
it
so
also
you
work?
have okay, I understood your question. So if I have a point A and a point B, and I want to have a middle path so that there is the path also goes from the middle point to the end point. So what I would do is I would give the point more importance in the cost function. I would give it a negative cost. So what it would do is whenever I am searching for the end node, whenever I come across the middle node, there would be a negative cost to it. So the algorithm would prefer taking that path over any other path, and as the cost function would get minimized when I go over that point rather than any other point. So what that would end up in is that the path taken by the in Unity, the game object would take the path from the start node to the point of the negative negative cost, and then to the end node. So this is also called giving weights to the different nodes. So whenever we design an the A-star algorithm, there is also more deeper A-star algorithm which also uses weights. So the different nodes are given weights as to how much the path is preferred. So if I want to design a game and I want to make a road, fields, forest, and different water features like lakes, rivers. So what I would do is I would give more preference to the roads. So whenever my uh, NPCs want to move, they will move over the road first rather than going into the forest or into the fields. So that's how it is done. So if I want to give more preference to some node, I would give it more weight. A weight can be anything, and you can optimize it later in the algorithm, but it will prefer that node with the higher weight rather than going to the water or through the forest. So that's how it's done. You can add a point in between by either giving by also including weights. uh, I hope that clears the question.
And it also tracks moving objects.
Yes, even moving objects, because A star can be dynamic, and you already have the path to the uh, objects in the stationary space. So even if it's moving, the you don't need to calculate the complete path. Majority of the path would be calculated even if the object is moving. So even if it moves, the part of the calculation is still with you. So you will just add on to that. So even that is efficient.
Thank you.
Excuse me.
Yeah. Yeah. Good.
जैसे अभी हर्ष ने बताया कि
Yeah.
he wants to go from a particular path, वो
Yeah.
that may be a middle point, तो
Yes.
कांट वी यूज काइंड ऑफ दो बार हम यूज कर लेंगे ना ए स्टार एल्गोरिदम, एक
हाँ,
पॉइंट से उधर जाने के लिए फिर दूसरे पॉइंट से उधर जाने के लिए.
yes, even that works. That's a good point. Yeah,
Okay.
you can use it twice.
Okay, that was my doubt. So yeah,
Yeah,
clear.
yeah. You can just define in your algorithm how many middle points you want, and the A-star algorithm would just first take from A to B, then B to C, then C to D, and however many points you want. Even that's viable.
Okay. And और एक है कि
Yeah.
it prefers more diagonal path as compared to horizontal or any vertical path, right?
Uh, how I have set it up in Unity right now, yes, because in my in my use case, I want the object to go diagonally also. But suppose I was in a maze. In a maze, you can only take either the vertical or the horizontal directions, right? So I can
Yeah,
also,
yeah, yeah.
yeah, I can also restrict the algorithm to take horizontal paths, and the diagonal paths will not be calculated. So it can also work in a horizontal and vertical way. But how I have set it up is that it can take diagonals, and as you know, taking a diagonal is the shorter path than taking horizontally and then
Much
going
better way.
vertically. Yes. So again, using the Pythagoras theorem, we can know the distance would be less than going to the other two paths. So in this example, yes, it would prefer taking the diagonal path first and then the uh, straight paths. But if you set it up in a maze kind of structure, then it can also go horizontally or vertically.
So it
Yeah,
also
got
depends
it.
upon grid. So the more
Yes.
number of divisions in the grid, the smoother the of my path will be. Or
Yes. Yeah, even that, and also like I mentioned before with weights, you can also have not just integer weights but floating point weights. So what that means is I can draw different paths on my grid such that the middle of the path has higher weight, and like a gradient, it has lower weight when I go away from the path. So the path which the object will take will be uh, curved rather than straight through the path. So it can also take smooth paths that way. Yeah. So any more questions, guys?
Hello.
Yeah.
I wanted to ask if I can use this algorithm for doing the opposite task, like the inverse. Like I want to find the longest path in any case scenario. So can I use this algorithm?
Longest path, how like from starting point to the end node, but the cost should be high.
Yeah.
Not exactly, as the A-star algorithm is optimized to find the shortest path.
No, the
It
whole purpose is finding the shortest. Yeah, go ahead, Aditya.
Yeah. Yeah. So even if I take the node with the highest cost, what would happen is, as I said, the heuristic cost is the cost going from the current node to the end node. So what would happen is you would end up going farther and farther away from the node rather than going towards the end node. So it's kind of impossible to find the longest path from the A-star algorithm in the current scenario, because it takes into consideration the distance from the current node to the end node. So the inverse would not be possible.
Okay. Yeah. Got.
Yeah.
I mean,
And also
Krishna
another question
Santosh,
was,
yeah, I mean, when we speak about AI,
yes, ma'am.
the whole purpose is you want it to be intelligent. Now, until and unless you have a very very genuine reason, why would you like want it to be longest? Considering a practically deployed scenario, there's rare a chance of developing an algorithm to act otherwise. Given the dynamic scenes, the dynamic costs, the dynamic weights, it's always expected to toll down to the the smallest cost or the least one, and that's the whole purpose of it being intelligent. Now,
Yeah.
when you this is something, now when you put it up as an algorithm, one would only choose a longer relatively longer path if the cost function accordingly is you know relatively less. Did you get this point? For example, I'll give you a practical scenario. Right now in Katras Chowk, the road is the right turn which otherwise can be taken is not permitted. So I have but no option other than taking a longer path, right? Now, if you look at it from A star point of view, there wouldn't exist any path to take a right turn. So that waves out the option, and you ultimately will land to a longer path because the cost function is going to be relatively less, and the only option will be the longer path. Getting it?
Yes, yes, yeah.
Okay, so that's how you want it. You will, whenever you are trying to map it mathematically, if you still want the algorithm to take longer, trust me, the algorithm is going to still take a relatively shorter path when you take g of h and f of h. That means the path cost and the cost function. Getting it? Let's say
Yes,
you
ma'am.
want to go for a very long drive, right? It's a very scenic place. Let's say you're driving to Brown counties and you are looking for a cost function. Now, in such a case, you are, even if you are taking a longer path, the cost function, that is your enjoyment. Maybe you're mapping it mathematically. That's the outcome you're looking for it. And in that case, it is still going to be the best path as per A star. Got it, dear? Understood it practically?
Yes, ma'am. Yes, ma'am.
Okay, okay. Go ahead,
Yeah.
go ahead. There was second point as well you on your mind.
Yeah. Another thing I wanted to ask, Dijikra's algorithm, yeah, as far as I know, it does not work with negative weights.
Yeah.
So, is there any problem with the ASR algorithm if there is encounter of negative weights?
No. So, like I said earlier, also, like you can use negative weights as well because the Asher algorithm takes into consideration the cost. So, if you want a specific node to be prioritized, you can give it negative weight also. The sum of the G cost, the H cost, and the weights would be reduced if you give it a negative weight. So, even that is possible. It just depends on how you implement it in the end. So, in the current implementation, what I would do is I would just add another variable to the cost function, which is the weights. So I can also give it negative weights and positive weights. So if I give it some node a very high weight such that I don't want that part to be taken. So when the sum is taken, the sum would be such that that node would have a least priority, and the node with the negative weight will have the most priority, as the sum would be less than what it would originally be. So yeah, the path with the lower weight can also be prioritized in A star.
Okay, okay. Thank you.
Yeah, no problem. Any more questions?
Okay. Anything else? Do you want
No.
some sessions on some specific topics? Abhishek, go ahead, dear.
No, ma'am, I was saying no doubt.
No doubt. Okay. Prem, would you like to add anything? Okay.
No, ma'am, he has covered all things.
Okay, fine, fine. So thank you all the dear students. Okay. Keep on interacting, keep on sharing everything that you have learned. It's always very catchy when you hear it from someone, it always makes your job easy. Now that's what my generation experience always say. And I hope same do you have, because that's how we are going to keep mm, this spirit up, right? So thank you so much. Thank you, Aditya. It was a great work. And I'm sure everyone is going to have a lot of takeaways, as I did tell in the beginning, which necessarily has to be beyond the technicalities. Fine. So study well for your in semester examinations, perform very well. Let the result contradict in all the ways and don'ts to what your unit test examination result is. We want very good score. We want very good performance from all of you. So let's have a round of virtual applause for Aditya. Everyone, please.
Thank you so much, ma'am, and thank you everyone for attending the session. It was really nice to interact with you guys.
Okay, chalo. Bye everyone. Should I conclude the session? Yeah, there is a feedback form. Please do fill it up. It's very important you bring your experience on record. That helps us to keep on arranging such sessions. And above all, it's going to be a great spirit for Aditya as well. So, yeah, everyone, please fill up the form. It will hardly take a minute. Thank you, everyone. Stay blessed, have a
Yeah,
good
thank you,
weekend,
ma'am.
and study very well for the exam. We need to now improve the number of distinction holders, and I'm sure with your efforts, you will do it. Bye bye.
Thank you,
Thank you,
ma'am.
ma'am. Bye.
Okay, bye.